Hey ladies and gentlemen, welcome back. This video we're going to talk about entropy, and we're going to dive into this complicated abstract topic. Alright, and we're going to use a generic reaction. We got reactants, right here, reactants. Whatever your reactants are. And reactants are going to go to the products, of course. Now, when we talk about reactants, they have a chemical and physical properties. Like they're solid, liquid, they're gas. They have a color or they're colorless, right? And they exist under, your pressure, volume, temperature, can be concentration as well. Those are your macroscopic conditions, all right? Because if I change the temperature, it's different. If I change the pressure, it can be different, all right? And the products also have the same P, V, and T here, right? And maybe molarity if it's concentration. The question we're talking about today is, will this happen? Will the reaction occur? Does it work? Is it spontaneous or not? All right. And what does spontaneous mean? Does it happen without ongoing outside intervention? All right. And in Chem 1, we talked about enthalpy, delta H. And that had to do with heat inside or heat content. And so you had some reactants, and this reactants had some chemical potential energy. And if we do the process and the products have less chemical potential energy, right? Delta H was negative, it was exothermic, and heat was released. And we generally said those types of reactions are spontaneous. They're favorable, right? Because we look through the eyes of heat going into work. If the reactants have less chemical potential energy than the products, and to get the products we had to add heat, delta H is positive, it's endothermic, right? These are typically non-spontaneous, right? Cooking's a great example. If you go out to cook, let's say I go out to my gas grill with a drink with ice in it, I'm going to put the food on the grill because the food is a delta H positive reaction. I need to, whatever I'm cooking needs heat in order for the reaction to occur. The grill produces heat, right? Mine, in this case, is propane, all right? And so if we look at two examples that I just said, my drink with ice in it, or your drink with, ice cubes, if you're that way. If we're at 25 degrees Celsius outside, all right? Let's just happen to say that's what we have, right? The ice, the solid water, will melt. We know this, right? Even though delta H is positive 6.01. Why does it melt? That's a great question. Well, there's enough energy, enough heat around it in the surroundings of the ice and water or whatever you have that the solid water will begin to become a liquid. There's enough energy in the surroundings for that to occur. Propane and oxygen, that is a spontaneous reaction if activation energy is met, right? So if I go to my grill with my drink, my ice is melting as soon as I go into the, outside to do this. But we turn the gas on in the grill, we turn the burners on, and you can hear the hissing of the gas come out, but nothing happens until you light the gas. And whether you have that little button to push or it automatically does it, or you have to use a match or a lighter or whatever you do, right? That is, once activation energy is met, the propane will go. Now, if we go down and cool it down to, let's say, wintertime, and it's negative 5 degrees Celsius out, the propane grill works the same way. However, if I have ice in my drink, it's not going to melt, right? And all of a sudden that ice, solid water going to liquid water is non-spontaneous. And so we need to kind of talk about this and see what's going on here because, right, we change the conditions, change temperature, and things are changing. Even though delta H, for the most part, at least at our level, delta H is not changing with temperature, right? But something else is going on because I have, enthalpy is part of the overall change, but not all of it because that's positive, right? For ice melting, needs heat and it's spontaneous at 25. And that's negative at 25 and it's spontaneous. So let's look, all right, at this new function. All right, new function. Entropy. Ludwig Boltzmann came up with this. And it's how spread out or how dispersed the system's energy is. All right, and one of the reasons it's very abstract, we can't even calculate it. All right, so S equals K. K is the Boltzmann constant, named after himself, which is just the gas constant R, in the 8.3145, divided by Avogadro's number, all right, which is 1.38 times 10 to the 23rd joules per Kelvin. All right, so not a lot of energy per heat. Now, for this, for entropy, right now I was going to tell you entropy matters more, changes in entropy matter more at low temperature than at high temperature. All right, because as you can see, T is involved, right? You got joules per Kelvin in the unit. And so at higher temperature, the changes in entropy is not nearly as much as at low temperature. So if you're at very low temperature, a little bit of energy makes a big difference. At high temperature, it doesn't make as big of a difference. Kind of like when I was a college student, my dad handed me $20. That made a difference on what maybe I was eating that weekend, or what I could do. Today, now, my dad doesn't hand me $20 anymore. But if my dad were to hand me $20, that probably wouldn't change anything. In fact, I'd probably just spend it on him, or him and I, right there at the moment. It wouldn't change as much, right? Because that's just how that works. Because, if you give people who are very wealthy $20, it doesn't change anything, right? Yes, it's still $20, but it's not the same thing as if you don't have a lot. You make $5,000 a year, $20 all of a sudden now, right? And I've been there, and I made it, right? And so nothing wrong with it. I'm just saying, same thing with energy and the entropy. So if you have a little bit of heat at low temperature, it makes a bigger impact than a little bit of heat at high temperature. And then you get the natural log of W. What is W? W is the number of possible arrangements, the microstates. All right, I'm going to relate this to something you might have seen before. But X is the number of states. So if you have 4 molecules, 5 molecules, 6 molecules, right? Even just 2 molecules, right? Just 2 molecules in a bond. And the number of ways you can arrange those, right? If you 100 times, 2 to the 100 power, right? Now you're starting to get these numbers, or 200 powers, all right? Okay? It gets kind of crazy. But that's the number of states. And then you get the macro state, which is overall conditions. All right. And so when we talk about arranging things, what do we mean by arranging things? Okay. All right. We're going to leave it right here for a second. For example, if I have O2, if I have O and O, and I have the double bond in here, right? Okay, just one molecule. This oxygen here, or this oxygen can kind of go back and forth. Like this bond, think of it as a spring. It can be longer and it can get shorter. It can get longer and get shorter. It can do that. The bond can also vibrate a little bit, right? So you have the bond vibrating, right? So these two bonds can vibrate. These don't really rotate much because double bonds don't rotate well. Okay, but a single bond, even a single atom HH, H bonded to H. All right. What I mean by this is this H, this bond can vibrate over here, but it's also going to vibrate from over there too, right? So they can get bigger and smaller, all right? And now this one can rotate. And so those are different things that just a single bond can do, all right, when we talk about different states, all right? And so when you have lots of these molecules, different states, you can get a lot of different randomness, all right? And so entropy is kind of like randomness, how spread out or dispersed the system energy is, all right? And so the more random, the more dispersed. And so you talk about like macrostates and microstates. If we look at combinations and permutations from math class, all right? A lot of times we'll do combinations here because combinations for like O2 molecules, right? We have O2 molecules here, right? You can't distinguish them, right? They're not individuals. They're just O2 molecules. So if I have 30 seats, 30 states and 20 molecules, right? Let's say that combination is 30 million. All right, there's 30 different million ways to combine them in 30 spots. Now I could take that down, I could take that up, right, in the number of seats. A visual for you is more of a, would be a part, like permutation, right? So 30 seats and 20 students. That's how many ways you guys can be arranged. 7 times 10 to the 28th. So if you went to a class and you sat in a different spot, and everybody sat in a different spot the entire time, you never run out of ways to do that. Even if it didn't matter the order. Like, it didn't matter who you, like, you just, the ways to arrange the humans, right? If we just made it, instead of seats, individuals, like your names is just human in seat, it'd still be 30 million ways to do that, which is kind of crazy, right? And so when you're talking about a mole, if you have a mole of gas, 6 times 10 to the 23rd particles, you're getting to these numbers, so we don't really even calculate W much, all right? Because like my calculator here can't do it, all right? And so when we talk about these states, all the different vibrations and whatnot, rotations, all those contribute to like how dispersed the system's energy is. Now, the most probable state is the one that's the largest number of possible arrangements. All right? But W is difficult to determine. All right? So we've done some other things like standard entropy. So the standard entropy, all right, is the absolute entropy of a system at 1 atmosphere. All right? Now, when we talk about change of entropy, right, the delta S of a system or a reaction, right, is the final minus the initial, just like it was with enthalpy. They're both state systems. Right, here's for gas expansion with volume. You can also be with other things too. Your current book derives this. All right, so when we talk about, remember this means 1 atmosphere, 298 Kelvin, 1 molar for a solution. Right, entropies are always positive. Okay. So, because molecules have molecular motion, or atoms even do. Even atoms, right? They have atoms moving around. They got, right, again, vibrations and rotations and different states. So there's everything that has temperature has entropy. Solids have the least, then liquids, then gases have the most entropy for the same substance. Right? It has to be the same substance though, right? Okay, and so if it's a different substance, like if you look, if you come down here, I come down even more, right? Water, gas water has a lot more entropy in joules per Kelvin mole than liquid water, right? Heavier, neon has more entropy than helium, because neon is bigger. That's the only difference. Right, more complex structures have more entropy, and then allotropes. So here's some allotropes of oxygen. Oxygen gas, O2, and then O3. O3 has more entropy than O2 because you have 2 bonds versus 1 double bond. You have a double bond and a single bond for O3. So there's more bonds, there's more vibrations and translations and rotations that are possible, which means there's more entropy. All right? So entropy is kind of a weird concept if you think about it, right? It's kind of weird. It's this abstract quantity, really, a number of ways they can arrange a system. We can't see this. That's why I like the human, right? In the seats analogy. So obviously, if you have one person, right? If we go back up to this, even whether it's a permutation or a combination, if you have one person in one chair, right, there is no entropy, right? Because there's just one way to arrange you, and the natural log of 1 is 0. So there's no, yep, you're in your seat, and there's only one. If there are 2 seats now it's different. You have more entropy at 2, all right? 3 seats, 1 person, you got more, right? You got more options. All right, and as right, but each one of those is a different macro state. If I add another person, so you and a friend are in 3 seats, now it's different conditions, and so there's all these different ways that you're comparing. But as you get higher and higher up, like if you talk about you going to a lecture hall that has 300 people or 400 seats in it, right now the entropy can be huge, right? Because you can sit, if there's 400 seats and there's, let's say, I don't know, 30 lectures or 40 lectures or 50 lectures, you can sit in a different seat each time and not ever repeat, right? And you can sit next to, in these bigger lecture halls, right? You can sit next to different people in different seats every time. And so that's more entropy, okay? And so that's kind of what entropy is. Let's do a couple examples to put this down because, first we got to talk about, for a reaction, this is very similar to delta H, okay? And these are in the book with delta H, products minus reactants. Now, for processes like melting, vaporization, sublimation, temperature increase, and more gas molecules, delta S is positive. And then entropies are always positive. They're not zero, right? So if you remember delta H of O2, a lot of times people don't give that to you because it's zero, right? There's no enthalpy change, no delta H change with O2's formation. However, O2 itself has entropy, all right? And so this entropy thing, because the O2 is moving, it has temperature, it's going to have entropy. So let's look here at these 2 examples. First example, for which of the following physical processes is delta H positive? And that should have a question mark after the end because it's a question. Well, freezing ethanol, right? So if we have CH3CH2OH liquid going to CH3CH2OH solid, we're becoming a solid. And so if we look back up, solids have the least entropy and gases have the most entropy for a given substance. So we would actually be decreasing delta S here would be negative, not positive. Water, evaporating water, complete opposite, right? H2O liquid going to H2O gas. Well, delta S, it doesn't have to be at standard pressure and temperature. Delta S would be positive, right? Mixing carbon tetrachloride and benzene. So you would have C carbon tetrachloride, Cl4, plus, or going into, we'll just put plus, C6, not 6, C6H6, right? Now you have a solution, right? And that solution, delta S is positive. Heating water, more temperature, right? More temperature, delta S is positive, right? You're giving it more randomness. It's got more ability to rotate and bend and vibrate and all that stuff. All the bonds have more freedom to move. Bromine vapors condensing. So we would have Br gas going to Br liquid. That delta S would be negative because we're becoming more organized. So that's how you can approximate delta S, by looking at the process and what's going on. Here's another way we can approximate delta S. We want to see if it's positive or negative. Ozone going to O2. Well, if we look at this, we have 2 molecules that are O3 versus 3 littler molecules. Well, the 3 littler molecules, right, will have more entropy than the big molecule. That's just how that works, all right? So little molecules have more entropy than big molecules. All right. The next one, I have 4 irons and 3 oxygen gas going to iron 3 oxide. Well, I have a solid and a gas going to one bigger solid, right? And so if we write this down, for A, we had more gas. B, we have a larger solid. So A, delta S is positive. B, I'd say delta S is negative. 3, I got hydrogen peroxide decomposing to hydrogen and oxygen. So 2 molecules going to 3 molecules. Going to 3 smaller. I say delta S is positive. Here I have a solid and a liquid for lithium and water. And you now have a solution and gas. So solid plus liquid going to solution and gas. So I'd say delta S is positive. And then finally, I got ammonia, 2 ammonias going to nitrogen and oxygen. So I got 2 moles of gas going to 4 moles of gas. So I say delta S is positive. All right. So that would be a way you can approximate the sign of delta H, not the number, the sign. You can actually use the table, right, and come up with their actual numbers and calculate it, but that's how I would approximate it. So that's the basics of entropy, right? This organization of energy, so to speak. Is it dispersed? Is it concentrated? All right. And it's abstract object, abstract. Make sure you read the book on this one. That's very important to read the book on this one because it is a tough concept to wrap your head around. If you have any questions, don't hesitate to reach out. Otherwise, we'll see you next time, guys. Take care.